Let me identify a little bit of. We have mechanical engineering. And how many faculty members are in here? About 2, 3, 4, 5. And how many students? Let's say about 20 students, 20 mechanical engineers. And let's look at electrical engineering.
How many of them are faculty?
Right. So who is faculty? Two.
Electrical
Two. Okay.
Six students.
How many students?
Six.
6 students. Okay. You have computer science. How many faculty members? One. Just one? How many students? About 10. And the communication department. Communication department. How many faculty members?
We have EC, DC.
Okay.
Put together we have 3 faculty members and 14 students. Allah, EC. We have telecom also.
CNC, electronics and communication.
So
EC.
let's look at it like this.
Electrical sciences.
Electrical sciences will include electrical and electronics.
Electronics and telecommunication.
Right. So communication, let's put it as communication and telecommunication. The reason I'm trying to do this is I think we'll have a good idea looking at what we are trying to accomplish. It will be a nice thing to split up in this form so that we know what is the strength in each subsystem of a satellite. I'll talk about that. So communication, telecom plus communication.
31 students.
31 students. And how many faculty members? 3 faculty.
3 EC. No, now more.
6 plus 31, sir.
6 plus 31.
6.
How many from mathematics? One faculty member and one student. How many students?
Students.
All of them.
Instrumentation.
Electronics and instrumentation.
Nice. 4. I just want to get a general idea.
Information science, software,
Science and information. Computer science, information.
Information science plus MCA.
Plus.
How many should I add here?
3.
How many more students?
Yes. 5.
Total.
5 plus. CSA is there.
Can I get a better? So the goal of this this activity is, what we are going to do is, at least my intention is, I want the students to seek diverse and challenging careers. That should be our vision for this, for having this activity. What happens is, what has happened is, and I took this route as well. See, there are so many diverse fields, the best of these will try to go into IT field, right? Even regardless of what you learn, you'll try to go for a higher salary. I did that myself. For 3 years, I was a mechanical engineer. I got a degree in mechanical, and after that, I gave up my 4 years of study. Whatever I had learned for 4 years, nothing was useful when I joined as a systems engineer, software engineer at Tata Infotech. It was a very good job. It was a very good company, but my career was limited in that, and that is the reason I quit my job after 3 years. Came back, did my master's and a PhD in aerospace engineering, and it was a struggle for me to quit my job and then go back to school, get used to that. So what you should be motivated is try to stick to your field. There may not be a immediate, steep going up, but eventually that will be more fruitful, more satisfying, more fulfilling than just taking a job, a high-paying job. We are not seeking successful or fulfilling careers anymore, and that is one of the goals of this course. And the second intent is I want us to be aspiring rocket scientists. See, ISRO is doing wonderful things, but we need to complement them. We need to be able to understand. How many of you all will join ISRO? How many of you all are thinking of joining ISRO? I want all hands up. That is the reason you are attending this course. You may not join, but you should have the intention of joining ISRO. Why do you not want to join ISRO? Because they pay less? You should want to be rocket scientists. That is the reason we should all be wanting to join ISRO, right? The expectations. So what are the expectations of the course? What we'll do is we'll split up the grading. I'll just do the grading and give the grades to the faculty here for the students. I'll do the gradings for the students and give the grades to the faculty in case they want to do something with the grades. So the gradings, what we'll do is we'll have weekly reports. Okay. So weekly reports, all I want you to do for the weekly reports is just summarize what you have learned in the week. Okay? Summarize, give a good summary of what you have learned in the week. There might be one or two problems or one or two of this thing, but this thing should be just summarize. Is this visible to the people back there? You want me to bring the board ahead?
New pencil.
Okay. Am I audible to the folks back there?
Yes.
So we'll do a weekly summarize, and let's say we'll give this 30% of the grade. And then we'll have, at the end of this course, the different student teams. You'll split up into teams and you'll prepare design reports. Okay. These will act as a preliminary design for a potential mission you guys are going to work on for, let's say, 2-3 years from now. Okay. So this design report, each team will prepare a design report based on the subsystem you are involved in. And a student may be involved in one or more preparing the design of one or more subsystems. So that's okay. Alright, so design reports, what are the percentage of grade you want for the design report? About 40%? Is that good? And then you have design posters apart from preparing the design reports, you'll do a design poster. You'll do a, like let's say a presentation in the form of a poster. We can have a small poster session to conclude the course where you'll present what you have learned. And the faculty can evaluate you as to what you have done. All right? So this will be about 20%. And then your attendance will be about 10%. Do you want me to write bigger? Is it visible now? Not quite? I'll try to write bigger. So is this clear? Is this split clear? The weekly reports is 30%. Design reports is about 40%. Design posters is 20%. And then your attendance. So I'll request one of you to just pass an attendance sheet and just record the attendance. So attendance is 10%. These are the expectations of the course. And as part of your weekly reports, I may give you review articles. I'll give you some articles to review. You can review those articles and summarize those articles. The course outcomes you learn what are PNMSats, okay, what are pico nano micro satellites, or what are these containerized satellites. And then we look at how do we design, develop these different these PNM satellites. And why do we need PNM sats? Okay. I will emphasize a lot on this, on these three. Whatever we do, we should understand what are you doing today? Anyone? Can anybody answer? What are you doing today? What are you doing in this class today? Come on.
We understand the PNM satellite.
No, but what are you doing today?
Yeah,
Simple.
listening.
You are attending a lecture on PNM satellites. Simple. How are you doing this? By listening. You're sitting here and listening. Why are you doing this? This is the most important question you need to ask. Why am I doing what am I doing? This only justifies the purpose, the intent. So I will always ask you why you are doing something, right? And you have to be able to tell me, you have to be able to reason out and tell me why you are doing something. So this is, again, the course outcomes are based on this what, how, and why questions. Okay? So these will be the course outcomes. When When I say why do we need PNM SATs, everybody understands what PNM SAT stands for? So PNM SATs is a short form for pico, nano, and micro satellites. Most academic satellites will fall in this category, pico or nano satellites. Pico is, and they are defined by, I'll talk about that, but just to give you an initial idea, this is about a kg in mass, this is about 10 kgs in mass, this is about 100 kgs in mass. Okay? So anything greater than 10 kgs is a microsatellite, and that's the reason we include microsatellites. But most satellites, most academic satellites will fall in pico or nano category of satellites. Right? So when we talk about what are PNM SATs, we'll talk about these are the course objectives. I'll give you a very detailed or much better understanding of what these satellites are through a presentation. But let's focus on what the objectives are. These are the objectives of the course outcomes. You need to know, you need to tell me what are PNM SATs. You need to tell me how do we design, develop PNM SATs. And third is, why do we need PNM SATs? Now let's talk about this a little bit. And this will be our motivation for the launch we're going to get out of this university, of this institution. Why do we need satellites? Why do we need PNM SATs? Why are you becoming engineers or scientists or mathematicians?
Successfully accomplish the objective.
What objective?
That depends on many objectives.
Right. So what is that?
So something productive, something socially.
Why do you want something productive?
So because that's what matters at the end.
Right. You're getting there, but tell me, yeah, you're getting there. Think about why we do what we do. Why are you trying to? What engineering branch are you in?
Fulfill the need of society.
Huh?
To help the society.
To help the society. So we are always trying to do everything is we do has to benefit the society. Otherwise, there is no point in doing it, right? The societal benefits, and whatever branch of engineering you start studying, you'll probably go into the real world and try to better society, better living. So societal benefits is very key. So when we talk about societal benefits, we talk about make life better. And of course, being in an academic institution, what are the intellectual benefits? Is this visible? Alright. Let's wait for. So let's talk about societal. What kind of societal benefits does a satellite have?
We can reach out maximum area, maximum community.
But what do satellites serve? What is the purpose of satellites serve? Why would you launch a satellite? Many applications. Weather is one application. Right.
Earth exploration.
Huh?
Earth exploration.
Earth exploration, communication, disaster management. So there are many societal benefits of satellites, right? So when we design the satellite here, and one of the biggest benefit of satellites is education, actually. And we will try to do here. The reason we want to build satellite will be, of course, we want to benefit society, but at the same time, we have to benefit. We have to look for benefiting the academic or the education. Will you learn something? Will you get educated if you learn about satellites? Of course, right? You'll get that education, and that is what we are. That is one of the very important things we are trying to get out of this course. Not just learning how to build something, but we want to also impart education through the mission. Okay, and what all branches do you think are involved in satellite design?
All great design.
Practically all branches, right? Everything you do. Is there communication? Is there telecommunication? Is there electrical engineering in that? Electronics, information science, mechanical, civil.
Chemical.
There is also civil. You can apply civil engineering as well. So this is, if you look at engineering itself, engineering is, what is engineering? Application of
Application of science.
sciences and mathematics, right? So if you look at mathematics and science, when you apply mathematics and science, it becomes engineering for the societal benefits. So we're using all the branches, and that is the reason this course is relevant, right? If you study this, you're practically studying every branch. You know, you can go across branches and understand. There is, and I need to talk about this for a minute so that I want you to get motivated about this. Particularly in today's world, you need to understand. You need to understand the significance of interdisciplinary education. You cannot just concentrate on one branch. Then you cannot grow, right? Any aspect of engineering, it cannot exist by itself. What is the point of, for example, this computer, your cell phone is different parts of engineering, right? Now, if you know one aspect of engineering in there and not the other, you'll not know what the purpose of cell phone is. If you know just communication, you'll wonder, why do we need the casing? Does communication have anything to do with the casing? Can a casing block the communication?
Yes.
So you should understand different aspects of engineering. Any questions until now? So you understand why we are doing this course? We are looking at societal benefits. We are looking at making life better, and then we are looking at being an academic institution. We have to look at academic intellectual benefits as well. We want to learn something. We want to get educated.
So the second point, sir. How is life makes?
Right. So making life better, I can give you examples. Your cell phones, if you want to communicate, it may not make life better always. For example, TVs, Direct TV, or here it is Tata Sky, right? You know how Tata Sky works. Tata Sky is not, it doesn't come through a cable, right? If you
Even cable operator will also get the satellite signal and then they
right. So they redistribute. So there is a satellite always there up there, which is redistributing. Everything is being channeled through that satellite, and that's the reason you have to point your dish antenna to a particular. Have you guys seen the old TV antennas? Everybody here has seen old TV antennas. So where are they getting their signal from? The satellite up there, right? So they cannot get a signal from through a wire. So that is making life better. If you're using TV for, let's say, some academic benefit or some learning, is that making life better? That's making life better, right? If you're looking at weather, predicting weather, that is making life better. Communication, life.
Shall we constrain ourselves pertaining to our objective?
Sure.
Yeah.
What?
Means we are concentrating on launching a satellite.
Right.
So how we could make something better? What is that? We can
So when
define it.
Right. So let's say you identify an experiment for the satellite. Let's say you want to send, you're trying to figure out a cure for a disease, right? Now you have looked at,
At least we shall restrict ourselves
Mhm.
to make something good for community inside the SIT. I mean, student community inside the SIT.
right,
So we can concentrate on them rather than going for high objective like doing an experiment over there.
right. No, that's what. So you need not limit yourself to the SIT campus. You can do that as well. The direct benefit of something like this is
First, let us put up a small objective, so then
Mhm.
we can think of the higher ups.
sure. So what objective do you want to put for the campus?
We can have a brainstorm and we can define some objective.
Right. So what we'll do is when we talk about the mission payload, we'll have a brainstorming session. The mission payload, when we come to that, the mission payload is what you're talking about. So we'll have a brainstorming session. If you look at the course description, you will be required to figure out what you want to do, and let's say make a presentation here. That is part of the course system. So there'll be, let's say, 5 or 6 mission payloads, and then we'll among ourselves we'll take a vote and say we'll work towards this mission payload. So everybody is clear with the intent of the course. Any questions until now? No? You're good? We'll talk a little bit about, so this is the introduction part, okay? So we'll start getting technical, or we'll look at some of the technical background we need for this. We look at some of the orbital mechanics background. Most of you had some exposure to this as part of your physics, okay? But we'll take a formal look at what constitutes some of these things. Have you heard about Kepler's laws of motion? So Kepler's laws of motion, what is the significance of Kepler's laws? Anybody?
Planetary, we can understand planetary.
Planetary motion.
And then
But
force.
what, from the historical perspective, what is the importance of Kepler's law? Historical perspective, in the sense, I want to give you a little bit of history. Anybody?
Because you give the planetary force.
Right. So that tells you.
How to govern the planetary motion, and then how other planets are controlling the influence on other some other planets.
Right. Anything more you want to add?
Elliptical orbit as well as heliocentric.
Right. That is the correct. That is a technical, or that is the importance how to define motion, planetary motion. But up until Kepler came, Johannes Kepler came, whatever was being proposed was just hypothesis, right? Like the sun is in between, the earth is in between.
Then they are flat. Earlier
They were assuming a flat surface. So when Kepler, you know what a law is?
Kepler law.
What is a law itself? Set of rules, right? So how do we use, what is the limitation of physics and mathematics? What is the limitation of mathematics? So this law Now what I'm going to tell you here is, up until Kepler came, whatever was being proposed was just philosophy without any proof, right? When Kepler, and this was, I'm talking particularly of planetary motion, there were many theories which came up from the Western world. I think I want to believe that we always knew the laws governing planetary motion, but from the Western world up until Johannes Kepler came, everything was just philosophy about planetary motion. Theories put forward. Some were with. When he came, he gave laws of motion, which means these could be constantly proved, right? And now tell me, what is a law? Why do you need a law? So if you look at the intermingling of physics and mathematics, how do physics and mathematics intermingle?
Brings certainty to the concept.
Can you prove a law? Can you mathematically prove a law?
Yes.
You sure? Can you mathematically prove Newton's first law? You cannot mathematically prove a law. Law is the starting point. Law is accepted as it is. You cannot mathematically, of course, when Kepler came, Kepler's first law couldn't be proved mathematically. It was a statement, it was a mathematical statement, right? So starting with Kepler's law, you could prove 100, you could do mathematics on that. But you couldn't really prove, you cannot mathematically prove Kepler's first law. But that is until Newton came, okay? And I'll talk about that. So Kepler's first law states the orbit of each planet is an ellipse. With the sun at the center, focus. Okay. What is the difference between focus and center? There are two foci and one center. So the sun is never at the center. Don't make this mistake, right? So this orbit of each planet is an ellipse. How do you draw an ellipse? Have you guys? Can you draw a perfect ellipse? How do you draw a perfect circle? You take a
Radius.
What is the instrument used? Compass. How do you draw an ellipse?
You have to tie the rope and then you can.
Right. So when you draw an ellipse,
At the end.
you need two compasses or 2 points like this. You tie a string
Then
and you stretch it. You do this, right? You tie a string around this and stretch it. You'll get an ellipse. What are these 2 points? So the sun is at the focus. And what is happening here? That is the orbit. Okay? The orbit of each planet is an ellipse with the sun at the focus. This is what he stated. And you have to give a lot of credit when you talk about Kepler's motion. You have to get a lot of credit to Tycho Brahe. Tycho Brahe was the person who actually took the measurements. He did at least 10 years of work before Kepler proposed his first law. And then he analyzed more data and it took many more years to propose his second and third law. What does the second law say? So the line joining, and this is important here because we are talking about satellite, planet, the sun sweeps out equal areas in equal times. Now, just notice this thing. This S here is capital. Why is that? Sun is a star, right? It's the name of the star. Our solar system, the name of the star of our solar system is Sun. So when you write this S, you have to use capital S. Similarly, when you use Earth, whenever you write Earth, don't use small e. Use the capitalized E, because Earth is a planet. It's the name of a planet, right? So this line joining the planet to the sun sweeps out equal areas in equal times. Now this is interesting. I'm going to draw this ellipse. What axis is this? Major axis. What axis is this? Minor axis. Now these are the fourth axis. So typically what we do is we call this F and we call this S star. Okay? This is the occupied focus. What is here with regards to the Kepler's law? What do you find here? The sun. What is happening here? The orbit. If you look at, let's say this is the sun, okay? This is Earth here. Anybody knows what this point is?
This is perigee.
Perigee or periapsis. So if you're looking at this as the sun at the focus, do you agree that this is the point of closest approach? This point is closest to the sun. So that the general point for any two bodies, right, is called the periapsis. You understand? So we are talking about sun and earth, earth and moon, earth and satellite. The general point of closest approach for the orbiting body is periapsis. If the discussion is sun and earth, this is
Perigee.
perigee. Perigee, G is for earth. So this is actually, this is not perigee. This is actually perihelion. Because this is sun. So we go by the central body. If the central body is sun, it is perihelion. If the central body is earth, it is perigee. Then this would be a orbiting satellite or moon. If the central body is, so we go by that. Okay. The general term is periapsis. Can you tell me what is it for moon? If the central body is moon, can you guys look it up and tell me? Huh? Moon cannot be at center? Why not? We don't launch anything. We don't launch moon orbits. We don't launch lunar probes. We do launch lunar probes, right? So what is at the center then? Moon. Right? So yeah, moon can be at the center. Now you have to understand something. Is there anything that doesn't have gravity? Do we have gravity? Of course we do have gravity, right? So anything can be centered. It's just that somebody may not revolve around you. Even if you have gravity, right? Somebody may not revolve, but everybody has gravity. Anybody and everybody can be a central body. Okay? So what does, you understand this law in this context, the first law, correct? What does the second law say is, I'm going to do this, T equal to T0. Is this visible, folks at the back? So I'm going to say this is T equal to T0. This is time instance T0. This is time instance T1. This is time instance T2. So Earth is going like this. Okay. Now I'm going to call this as dA2, this area. This is dA1. Alright. The second law states that dA1 by dt1 is equal to dA2 by dt2. Right? So what is, how do you calculate dA1? Area of sector, right? So you just have to do the this one and you half length into the sector dimension, right? So dA1 over d2. Now going by that, tell me, can you correlate the speed of the orbiting body?
It will be more at
Perigee. Why is it more at perigee or perihelion or periapsis? Anybody?
force of attraction will be more.
Just by that law. Now, don't go by your, if you know that it is faster here, that's fine. But just by law, can you make out something about the speed? Just looking at that law. Yes. So if you look at this area, let's take this area. Okay. Now let's assume this is dA V. Let's assume dA3 is equal to dA2, right? So to cover the same amount of area, because the length is greater, the radius is greater, it will have to go slower here from this point to this point. It will have to go much faster here. So the speed is fastest at the perigee, and it is slowest at the, what is this? Apogee. Okay. So these are, let's not call this apogee. What is this? Apoapsis. Alright? Apoapsis is the general term for any two bodies. For if sun is at the center, it is apohelion. If sun is at the center, if Earth is at the center, it is apogee. So this is what it means, that here the speed is fastest and here the speed is slowest. Okay. Do you feel that with Earth? Why don't you feel that with Earth?
Because we are relatively on the ground. That is why we will not feel that.
That to some extent.
Because it's not a sudden jump, it doesn't teleport from here
perhaps is the change is gradual, so we don't feel because the
Okay.
relative motion is zero between us and the.
What do you know about the Earth orbit around Sun? It's actually pretty
Tilted.
close to a circle. It is an ellipse, but it is not a very
Almost circle.
not a very high centricity ellipse. It's almost a circle. So the speed is not as much. So we don't notice it as much. Okay. So this is second law. The third law. The square of the period
Proportional.
is proportional to
Earth.
So this is the third law. It states that the square of the period of a planet is proportional to the cube of its mean distance. What does this mean?
Average.
Why do we talk about mean distance?
Because it goes on varying.
Right. So distance keeps on varying. That's the reason we need to talk about mean distance. Okay. The square of the period. What does that? If we were to indicate, p square is proportional to
Earth.
a cube. What is a?
Semi-major.
Semi-major axis. Okay. Semi-major axis is typically this distance is a. This semi-major axis is actually the mean distance. If you look at the ellipse. So the period. What is period?
Time taken.
Time taken for an orbiting body to complete one orbit. Okay. So this is the relationship. Now, what does this relationship tell you about orbits, or what does this relationship tell you about the altitude? The farther you go, what happens to the time period? It increases, right? So can you correlate? What is you have all heard about geosynchronous or geostationary orbit, right? You know what a geostationary orbit is?
36.
Geostationary orbit is
4164 kilometers from the time.
the time period of a geostationary orbit is
24.
Same as
Same as Earth.
same as Earth of what?
rotation.
Rotation?
Yes.
You sure? Geostationary orbit, what is the time period? 24 hours?
23 hours, 56 minutes.
24 hours, you're right. So what is happening is, while Earth is rotating, the geostationary satellite will have to keep on, the relative motion is 0. So that is the time, because the time is 24 hours, which is so many seconds, this distance has to be that precise. Only then you're going to get that 24 hours. If you increase it, what's going to happen? It's going to go off, right? So that is the reason when you launch a geostationary satellite, it has to go at that precise location. What is the usefulness of geostationary satellites? What are some of the things we
Continuous communication.
continuous communication? What else?
Pointed,
Applications? Any applications of geostationary orbits? Oh, satellites?
same
Huh? Weather forecast for a particular region, right? What else?
communication.
Communication, TV. This thing has to be if you're GPS, GNS, or our GPS satellites. They have to be geostationary. Otherwise, you cannot get that location. If they are off, you cannot communicate. Okay. So this is what the law of period. Okay. These were the three laws which Kepler came with, and we really have to. This is important because when we launch our own satellite here, we have to visualize. Now, are you guys visualizing this in an orbit? You have to live here physically, but you have to live in an orbit in your minds to be able to understand what the satellite is doing. Right? We may not be able to launch a geostationary satellite here for the first time. We will launch something in the relatively low altitude orbits. Okay, I'll talk about what low altitude orbits are, but it will be much lower altitudes. So that time what happens is it is going to go
Faster.
much faster. Correct? If this distance is slower, then it is not going to rotate or orbit at the speed of Earth's rotation. It's going to go much faster. When Earth completes one rotation, this would have a low altitude orbit would have completed several rotations or several orbits. So every time it goes over, let's say we launch something and we are trying to track something here at SIT, there's only a small window in which you can track, like 8 to 10 minutes, 10 to 12 minutes. Correct? During that time, you have to do all the communication. Everybody is clear with these laws? You understand? Try to remember these, try to visualize these, think about these every day. All right? So now you have to almost switch yourself. People who work on Mars mission. What is how does their day function? Their days are not 24-hour days. They actually work 25-hour days because they have to keep up with Mars's day. So when you have to switch on to that mode where you're constantly thinking about orbits, how your satellite will be in orbit, what it is going to do in orbit, how you're going to control it in orbit. So that is now you have to switch on. Only then you switch it off once you have done with your mission. You come back to Earth only after that. Okay. So let's talk about Newton's laws a little bit. So Newton, one of the first laws he introduced was universal law of gravitation. And what does this say? That there's a force of attraction between any two bodies, and the force of attraction is directly proportional to the product of their masses and inversely proportional to the square of the distance. Right? So F is proportional to mn divided by r square. Now, if I use this, this is a vector. You understand what is the difference between a vector and a scalar? Everybody knows, everybody has memorized that a scalar has
Only magnitude.
magnitude. Vector has both magnitude and direction. But what do you mean? What do you physically understand?
larger body mass attracts the smaller body. That is why the force of attraction
Is that
towards
only larger body? Will the smaller body also attract? It will attract, right? So when we talk about, right, go ahead. There is a force of attraction in this direction, and there is a force of attraction in this direction as well. Which is greater? They have to be equal, right? So this force, there's a force of attraction between these two bodies. The force of attraction, if I do this is the force of attraction of the larger body because of from the smaller body towards the larger body. Got it? This is the force of attraction of the smaller body due to the larger body. So when we talk about vectors, you have to understand what that direction is. And this R we define, typically what we do is, we will define this R as the distance of the relative distance of the smaller body from the larger body. Right? Does that make sense? This is Newton's universal law of gravitation. I won't go into all the laws because for this discussion, Newton's first law and Newton's second law are relevant. Is force a vector or a scalar? Vector, right? Mass? Scalar. Weight? Vector. Then we talk about second law of Newton's second law of motion. So this is the first law, the law of gravitation is simply called the universal law of gravitation. Okay? The three laws are called laws of motion. So when we talk about laws of motion, what is the first law? Just for the completeness, let me talk about the first law. A body continues to stay in its state of rest or of uniform motion unless acted upon by an external force. So why does this not stay in motion? The external force is the friction. Okay. So is there friction in space? What is the friction in space? Vacuum is a friction? Vacuum is not a friction, right? If you talk about lower orbits, there is still some atmosphere. Keep in mind. If you keep going higher and higher, the atmospheric density reduces drastically, and that's when you'll experience vacuum. But strictly speaking, is there pure vacuum anywhere? It's only relative. Okay. So when we talk about a body staying in motion, the first law, everybody understands inertia as such. What is inertia? Inertia is? Yes, so that itself is inertia, right? So if we sit in a place for too long, we don't feel like getting up. So that itself is, when we are resting, we don't feel like, do you feel like waking up any morning? Never, right? So the Newton's first law is that. Second law, what is Newton's second law? Now most of you will get this wrong. Newton's second law? Huh?
The force is directly proportional to change in the momentum.
Change in linear momentum, right? So can I say this? Can I represent? Is this right?
Yes.
Is this the same as?
Yes, sir.
How do you define momentum?
mass.
Mass. So this is change in linear momentum, right? Is this complete? So this is not complete. Okay, if you look at this, this is actually, how do you take derivative of this? You have to do this, right? Right. So unless, now keep in mind, this is very, very critical, very important. Rockets won't work if you use this. Okay, rocket will work only because of this. How does rocket work? When, what is creating the force? Huh?
Propellant.
Why should it create force?
Just to escape from the
What is the law which tells that it should create? How did somebody figure that out? Newton's third law when it is on the ground. I agree with you that when it is on the ground, it is pushing like this, the ground is pushing back, right? But once the air cannot push it that much, right? Once it is mid-air, the air cannot push it so much. So what is happening that it is thrusting? It is leaving mass out. There is mass loss. This m dot is causing mass loss. That mass loss is causing thrust. So whatever direction the mass loss is, what direction is the mass loss? If you want to go this way, the mass loss has to be in the opposite direction. So that is causing thrust. Okay. So rockets function like this. If you want to do orbit maneuvers, thrusters, you know, understand satellite thrusters? Satellite thrusters work on this principle. So when a satellite is orbiting in vacuum, there is nothing to push it back. Third law may not function there, right? So there, this mass loss is causing a force, thrust, which is thrust, and that is causing the satellite to move away. Okay. So this is the complete Newton's law. Keep in mind, this is Newton's law. Newton himself stated, ironically, you all knew that Newton was the one who, we believe that Newton was the one who gave us calculus. This is calculus. This is differential equations. You understand this is differential equation? What differential equation is this? What order differential equation is this? First order. Is it a first order differential equation? All right. So let me. It's a first order differential equation in velocity. It's an algebraic equation in acceleration. It's a second order differential equation in displacement. F is equal to m x double dot plus m dot x dot. This is a second order differential equation, right? So this is a first order differential equation, correct? Right? And finally, if I just write it as this, is this a differential equation? Is this a differential equation? It's a algebraic equation. So you have to look, when you talk about differential equation, you have to identify what is the differential equation in. Whether it is differential equation, whether it's position, velocity, all these are states, right? Physical states. Now when we combine this, and I can discuss the math behind this offline, when we combine this, what we get out of it is, which is a driving this thing for our discussions, we get the two-body motion problem. We can define the two-body motion, which is r double dot plus when we talk about here, okay, this is the two-body statement. When you combine these two, and I can discuss the math offline again if you want. When you combine the universal law of gravitation and Newton's second law, and with assumptions that these are the assumptions. Under these assumptions, if you solve these or if you do mathematics on these, you will end up with this two-body problem statement. Right? What is mu here? Mu is the gravitational constant. And this varies with respect to the central body. Okay? So this mu is different for Earth, Sun, Moon, depending on what is the central body. Now this is a second order non-linear differential equation, right? In the relative position. Okay. It so happens that there is no calculus-based solution to this problem or this differential equation. What is the process of engineering? Anybody? Where does physics and math come into play in engineering problem solving?
Realize the concepts into set of equations.
Yes. So you look at real world, you see a problem, right? As an engineer, what you'll do is you will try to formulate that. You look at what laws can I apply to that problem and formulate a mathematical statement, right? That is this mathematical statement. So they looked at the problem, applied whatever laws they could apply, and under assumptions, this is the problem statement that came out. The process is you apply physics, look at what laws you apply and formulate a mathematical problem. Then you forget about all the physics behind. You can use purely mathematics to solve a mathematical problem. And then you take the solution and you can interpret it based on what is the problem you have solved. So this is the problem. And the solution to this problem, now again I want to emphasize that there is no closed form calculus based solution to this problem. Right? So if you ever want to take up mathematics seriously, or if you go out there and give a closed form solution to this, a calculus based solution, you'll probably get an overprice. Okay? And the solution, it so happens that this is a solution solution is h square over mu multiplied by 1 over 1 plus e cosine theta. Here, so if you look at this, so if you look at this, the solution to two-body problem, you can again do some algebra on this and get to this point. You do a couple of dot product and cross product operations and you can get to this solution. Now it so happens, this is also the equation of a conic section. You know what a conic section is? Anybody? What is a conic section? Yes, absolutely. So you have this cone, right? Look at this cone. If you section it like this, what are you going to get? A circle. If you section it in an oblique way, you're going to get a ellipse. If you section just one of these, you're going to get a parabola. And if you section this, you're going to get a hyperbola. So this is where you have to sit down and see. For most of us, it is, when I was studying this was so amazing that even to think about going from suggesting something as universal as this, right? Try to appreciate this. When Newton came up with this law, it is so simple. You would look at the universe and can you just suggest this? Can your intuition come up with such a simplified explanation of, he was trying to define God, right? He was trying to understand God. He was going to give a mathematical expression for God or something like that. So he came up with this, he said, this is the universal law of gravitation. You apply this to anything and everything and you'll get any solution you want. It's very, very difficult to, and that is the reason he has the place he has. Because he sat, the Apple thing is just a coincidence, but whatever happened before that, he just simply threw this, that this has to be it. And until Einstein came along, we didn't want to believe anything else. Right? We accepted it like, we accepted it more than any of the religious texts. Okay? So this law, you combine this law, his first three laws, the laws of motion, were also very significant. That you could explain anything and everything, especially the macro, this thing. We couldn't explain anything that was traveling at the speed of light, but anything that was not traveling at speed of light, we could resolve. We just applied some extension, some form of the first three laws, and you could explain the world, right? So he took these two, right? He did some math on this. He came up with this. He worked this, and you could see that. Now tell me, do you see Kepler's law in here? This is two body motion. Okay. So this is what this means is you understand this problem statement of the mathematical aspect. Can you correlate the mathematics and the physics of this? What does this mean? So this is trying to define this is the statement for the trajectory of small m with respect to capital M. Is that clear? The trajectory of small m with respect to capital M. What is the path being taken? This is that statement. This is a mathematical statement defining the problem. This tells you what that actual trajectory is. Right? So here you got to, let me make this. So here, does this make sense? This R is a function of time, right? And this theta is a function of time. Everybody can see this theta? You guys? You know what LLP is? Anybody? Lord of lost benches. So you guys all will get LLPs. Alright, so I just wanted to. So do you guys see this? Everybody is able to see this? No? Back there. You sure? Now tell me what is can you correlate this one and this one? This is a problem statement defining the trajectory of this M. Okay? How is the trajectory? What is the problem defining the trajectory? And this actually gives you the trajectory. The trajectory is what?
The path traced by the.
So it's a path traced by M with respect to, it's the path traced by small m with respect to capital M. What is that trajectory according to this?
Orbit position.
What is that trajectory?
Any
It is one of these. You understand? The trajectory, the path traced by this is one of the conic section. It is either a circle or an ellipse or a parabola or a hyperbola. What did Kepler say? Ellipse. So Kepler's law, now you see Kepler's law ceases to exist as a law because it can be proved using Newton's law. So Kepler's law now becomes a special case of Newton's law. Are you able to appreciate that? So Kepler only talked. So right. So h is constant, mu is constant, E is. So I'll talk about. Let me talk about that. So when eccentricity, what is eccentricity? So eccentricity, when E is equal to 0, the conic section is a circle. When E is E is equal to 1, it is hyperbola. Okay, and what we're talking is you look at the power of Newton's three simple equations. What he stated was, and this is what really this was so this thing that when did Newton state his laws? Around 1600s, mid 1600s. Okay, and when did we launch our first satellite?
1952.
50s, right? Late 50s. So 58, I think 57, 58 was when Sputnik was launched. Now, can you see the power of Newton's laws? If we stuck to Kepler's laws, what would we have stuck with? We would have stuck with sun and planets. We would have never thought that if we launch something in space, that it would do the same thing as any planet or any this thing, right? So Newton told that forget about sun, planet, moon, or Earth and satellite. You still apply for anything, and that is what told us that if we launch something in space, it will behave just like what planets are behaving around the Earth or Moon is behaving around planet. Okay? And that is what he told. And he also said, not just the trajectory need not be just an ellipse. It could be a parabola, it could be a hyperbola, it could be a circle. So if you look at comets are highly elliptical orbits. What do you mean by highly elliptical orbits? Yes, so the eccentricity is much closer to 1. So they appear only, so it's like this. Right? It's only going to come, and your Earth is, so if I talk about this, your Earth is somewhere here. Okay? Once in a while the comet is going to come there. And your Russians have designed the Molniya orbits, which are highly elliptical orbits. If you want to command the satellite, if you want to give the instructions and send it really far, right? You can do that. So these comets will reappear only once in a while because they are in really highly elliptical orbits. Hyperbola, you've heard about flyby, what ISRO did with its Mars mission. It used the gravitational force of another planet to do a flyby, right?
It will go.
Yes. So what it does is it will. So if you're looking at even moon mission, so these hyperbolic orbits, you do a slingshot. So you go around Earth and then use the some planet and use the gravitational force of that planet to slingshot and go farther, much farther. Okay, and that is what ISRO did with Mars mission, and that's the reason they could get there with much less fuel. So you understand the significance of this circle, ellipse. Now you see why. What is a law? Are you able to appreciate what is a law and what Newton contributed? Right? So Newton gave you something very simple yet so powerful that any and every law, a lot of the reason we are all sitting here, I know some of us are cursing, why did he do that? We could have all been just eating and sleeping. These buildings wouldn't have existed if Newton had not come along. So a lot of developments have been possible, and that is the reason you should take pride in something like satellite design. All your technology, your phones, TV, has all been possible because people have been so curious to study celestial bodies. All the mathematics which has come out, all great mathematicians, especially the classical physics we talk about, has been possible because we were trying to study the motion of celestial bodies, planetary bodies. Right? So if you look at this, what is this theta? Now tell me, how do you correlate this and we have this is your F and this is your orbiting body. This is your perigee. This is theta. Is theta changing?
Yes,
With respect to time. So we say theta is a function of time. What is R?
radius.
R is the r is the position vector of the orbiting body with respect to the central body. You have to keep in mind it's not, I'm talking about the vector r. Okay? Here, is it a vector here?
Yes, with respect to time, it's changing the direction.
It's actually not a vector as such, but the theta will give you that vector phi. Okay. So this, the magnitude is defined by this. The theta will define the direction. Okay. So this r is this. We'll talk about this. So we also will always talk about r as the position of the orbiting body with respect to the central body. With respect to central body is very, very important, because is there anything absolute? So what was the assumption Newton gave us to follow his, what was the premises of Newton's laws? Does anybody remember? When he gave his 3 laws of motion, where does Newton's laws of motion apply? Inertial frame. You know what an inertial frame? Everybody understands. So this is a very important premises. Newton's laws only apply in an inertial frame of reference. You know what an inertial frame of reference is? Non-accelerating frame. Is there a non-accelerating frame in the universe?
Yes.
Where? Is anything moving at constant velocity? What is Earth? Is Earth moving at constant velocity? So we say acceleration due to gravity, right? Acceleration due to gravity. So gravity and acceleration are related. So everything is accelerated. If it doesn't accelerate, what happens? It will spiral in, it will fall inside. So there is a, if you're looking at, so something is orbiting, right? It cannot, there's a gravitational force pulling it as well. If it is not accelerating, so think about it, you're trying to run and somebody is holding you, right? If you just don't accelerate, what will happen? That person will be able to pull you back. If you don't, if this doesn't accelerate, this will spiral in and fall. Because it won't, there is no force which will stop it from being pulled by the gravitational force. There are 2 components, so this has to have 2 components. One component to keep it in this orbit, right? The other component to escape the gravitational force. So if you take a string, right? If you take a string and tie a stone to the end, when you're doing that, there are 2 forces which are keeping. One is the force, radial force, which is keeping it from pulling it back. The other is one which is allowing it to keep in that orbit. There is always gravity, there is always acceleration. You cannot practically think of anything that is non-accelerating. In the universe, can you think of what is not, for example, sun? Is sun not accelerating? As a solar system, we are probably orbiting a center of there is probably a black hole somewhere where we are orbiting, right? So there is acceleration due to that. So there is, every body is accelerating, is moving around something. So there is acceleration. So where is this non-accelerating frame? If we don't have a non-accelerating frame, why do Newton's laws apply? We are very comfortable applying Newton's law. Like anybody will say, let me prove it with Newton's laws. And you'll instantly prove it. So the accelerations, it so happens that for practical purposes, we can assume that the Earth's surface for example, is non-accelerating. Newton's laws will not apply, for example, in a aircraft. If an aircraft is if it's accelerating, Newton's laws won't apply. If you try to apply, you have to apply Newton's laws relative to if you want to apply Newton's laws in an aircraft, you have to figure out a inertial reference frame where you can define the position of the aircraft. So the inertial frame has to exist on ground or on earth. Right? Any questions until now? So let me just talk about orbital. Or you want to take a break and come back? Alright, let's come back at 1:30 after lunch. So I don't want anybody sleeping. Okay? Is that clear? So you better don't have a whole lot of food. Just have whatever is needed to keep you sustained. Any questions so far? No questions?